Have you ever wondered why some roads buckle under pressure? Or why massive building foundations settle unevenly, costing construction companies millions of dollars in unexpected, catastrophic repairs? The answer usually isn't the concrete or the steel. The answer is almost always buried right underneath your feet. It's the soil. If you don't know the exact characteristics of the ground you are building on, you are essentially building a house of cards. And the single most critical characteristic you need to lock down before a single drop of concrete is poured? The specific gravity of that soil. Welcome back to Certified MTP, your #1 trusted source for material testing equipment and construction testing supplies. Today we are diving deep into the absolute core of soil mechanics, specific gravity. We are going to explain exactly what it is, why your project's structural integrity depends on it, and most importantly, how to accurately determine it using the industry's top 3 pieces of testing equipment. By the end of this video, you will know exactly how to use a picnometer jar, a Latalier flask, and a complete specific gravity bench to get the flawless data you need. We'll break down the complex science into simple, actionable steps so you can guarantee the safety and stability of your next build. Let's get to work. Before we touch the equipment, let's define the concept simply. What exactly is the specific gravity of soil? In the simplest terms possible, specific gravity is a ratio. It is the weight of a given volume of soil solids compared to the weight of an equal volume of pure water at a specific temperature. Think of it like this. If a handful of soil particles is exactly 2.5 times heavier than the exact same volume of water, the specific gravity of that soil is 2.5. Simple, right? But why does this simple number matter so much in the real world of construction? Because specific gravity is the master key that unlocks every other critical soil calculation. You absolutely cannot calculate a soil's void ratio, its porosity, its degree of saturation, or its critical density without first knowing its specific gravity. If your specific gravity numbers are off, your void ratio calculations are off. If your void ratio is wrong, your estimates for how much that soil will compress under the weight of a skyscraper will be completely wrong. And that is exactly how you end up with cracked foundations, sinking highways, and massive lawsuits. Different soils require different testing methods based on the size of their particles. Fine sands require different tools than coarse aggregates. That is exactly why we have specialized equipment. Let's break down the first essential tool in our arsenal. First up, we have the picnometer jar and brass top set. This is the absolute go-to standard for determining the specific gravity of fine-grained soils, like sands and fine clays. Let's look at the design. It consists of a glass mason jar, usually a 1-quart capacity, and a precision-machined brass conical top. Notice this small hole right at the apex of the brass cone? That's not a manufacturing defect. That is the secret to the whole test. That tiny hole allows air and excess water to escape, ensuring that the volume of the jar remains absolutely identical every single time you fill it. Precision is everything. So how do we use it? The explanation is incredibly simple. We are basically doing a comparative weight test. Step 1, you take your clean, completely dry picnometer jar with the brass top on, and you weigh it empty. You log that number. Step 2, you take your oven-dried soil sample, usually around 500 grams, and you place it inside the jar. You weigh the jar again. Now you know the exact weight of your dry soil. Step 3 is where the magic happens. You fill the jar about 3/4 of the way full with distilled water, but here's the problem. Soil has tiny microscopic voids filled with air. If we don't get that air out, our volume calculations will be ruined. The solution? We agitate it. You can apply a gentle vacuum or carefully boil the jar, rolling it to release all those trapped air bubbles. Step 4, once the air is completely gone, you fill the jar with water all the way to the very top. You screw on the brass top. The excess water will squeeze right out of that tiny hole in the cone. You wipe the outside completely dry, and you weigh the whole thing. Finally, step 5, you empty the jar, clean it perfectly, fill it entirely with just pure water, put the top on, and weigh it one last time. By plugging those weights into a standard formula, You calculate exactly how much water the soil displaced. And boom, you have your specific gravity. It is a bulletproof, simple method for fine soils. But what happens when you are dealing with hydraulic cement, dust, or certain types of ultrafine sands that might react chemically with water? You can't use the picnometer with water because the material will hydrate and change right in front of your eyes. The solution to that problem is our second piece of equipment, the Latalier flask. Look at the shape of this glass. It has a wide bulb at the bottom for stability and holding the bulk of the liquid, and a very long, very thin neck. That thin neck is deeply engraved with graduated volume markings. Because the neck is so narrow, even a microscopic change in volume creates a highly visible change in the liquid level. It is built for absolute extreme precision. Here is the simple explanation of how you use the Latalier flask. Because we can't use water for reactive materials, we use a non-reactive liquid, usually kerosene or naphtha. Step 1. You fill the flask with kerosene to a point on the neck between the 0 and the 1 milliliter mark. You read that exact starting level. Step 2. You take a known exact weight of your dry test material, say 64 grams of cement or fine soil powder. You very carefully pour it into the flask. Step 3. As the solid material sinks to the bottom of the bulb, it displaces the kerosene. Just like getting into a bathtub, the liquid level rises up the narrow neck. You roll the flask gently to make sure absolutely no air bubbles are trapped in the powder. Step 4. You read the new, higher liquid level on the graduations. The math here is incredibly straightforward. You subtract the first reading from the second reading. That tells you the exact volume of the material you poured in. You divide the weight of the material by that displaced volume, and you have your specific gravity. It is fast, highly accurate, and solves the problem of reactive fine materials perfectly. Now we've covered fine sands and reactive powders. But what happens when you are building a massive highway subgrade and you need to test coarse aggregates? Large gravels, crushed stone, and heavy coarse soils simply will not fit into a tiny glass jar or a flask. The solution to high-volume coarse aggregate testing is the granddaddy of them all, the specific gravity bench with a complete 30-gallon tank setup. This is a complete standalone workstation designed for heavy-duty testing. It features a massive 30-gallon polyethylene water tank, a heavy-duty steel bench, and usually includes a suspension scale and a wire basket. It is built to handle the heavy lifting. The principle here is Archimedes' principle of buoyancy. We are going to weigh the large rocks in the air and then weigh them while they are completely underwater. Here is your simple explanation for operating the bench. Step 1. You take your coarse aggregate sample, which can be several kilograms of rock, and you soak it in water for 24 hours to fill all the internal pores. Step 2. You take the rocks out and roll them in a large absorbent towel until the surface is dry, but the inside pores are still wet. This is called saturated surface dry, or SSD condition. You weigh the rocks right there on the bench to get your SSD weight. Step 3. You place those rocks into a specialized wire mesh basket. This basket is suspended directly from a precision scale that sits on top of the bench, hanging straight down into that massive 30-gallon tank of water. Step 4. You lower the basket fully into the water, give it a shake to release any trapped air bubbles between the rocks, and you read the scale. This gives you the weight in water. Because water is pushing up against the rocks, they will weigh less underwater than they do in the air. Step 5. You take the rocks out, dry them completely in an oven overnight, and weigh them one final time to get the absolute dry weight. By comparing the dry weight, the saturated weight, and the underwater weight, you can determine not just the specific gravity, but also the absorption rate of the coarse aggregate. The bench makes handling these heavy, wet samples entirely seamless and highly controlled. To sum it all up, the foundation of your construction project is only as strong as your understanding of the soil beneath it. Knowing your specific gravity is non-negotiable. If you are dealing with standard fine soils and sands, the picnometer jar and brass top is your precise go-to solution. If you are dealing with reactive materials like cement or ultrafine powders, the Latalier flask will give you flawless volumetric displacement data. And if you are tackling coarse aggregates and heavy gravels, The specific gravity bench with a 30-gallon tank will handle the heavy lifting with ease. You cannot afford to guess when it comes to material testing. You need equipment you can trust. You can find the picnometer, the Latalier flask, the complete specific gravity bench, and thousands of other premium material testing products right now at certifiedmtp.com. Click the link in the description below to upgrade your lab and secure the exact tools we used in today's video. If you found this breakdown helpful and want more direct, problem-solving content for construction and material testing, hit that subscribe button, drop a like, and leave a comment down below on what test you want us to explain next. Build safe, test accurately, and we will see you in the next video.